Hello friends, I welcome you to my second lecture on Hilbert transforms. We are going to now discuss second alternative form of Hilbert transform pair. Let us recall that we had the question in the first alternative form, we had capital F theta written in this form. Capital F theta we had written in this form, and then we had combined these two forms and we got the first alternative form of the Hilbert transform pair by replacing phi y minus phi in the first integral. So, this was our first integral, and this integral now let us see, we can write like this. So, f theta equal to 1 over 2 pi integral over 0 to pi cot theta plus phi by 2 y phi d phi plus 1 over 2 pi cot theta minus phi by 2 y phi d phi. In the previous lecture, when we were finding the first alternative form, while finding the first alternative form of the equation 1, we encountered this equation. So, this equation f theta equal to 1 over 2 pi 0 to pi cot theta plus phi by 2 by phi d phi plus this can be expressed as 1 over phi f theta equal to 1 over 2 pi 0 to pi 1 plus cot theta plus phi by 2 y phi d phi plus 1 over 2 pi 0 to pi 1 plus cot theta minus phi by 2 y phi d phi. How we can do this? If you see, we can write it as if you recall, in the last lecture we had seen that 1 over pi integral 0 to pi y phi d phi, this we had denoted by c, and this be denoted by c. 1 over pi integral 0 to pi by phi d phi we denoted by c, and then we proved that one over pi integral 0 to pi by phi d phi equal to 0. By what we had done was we replaced by phi equal to small y phi minus c, and then we separated the two integrals and we got that this value is equal to 0. So, this can be if we add it here, we are actually adding 0. So, 1 over pi 0 to pi by phi d phi. If we add this here, actually we are adding 0, so there is no change. So, I can write it 1 over 2 pi, and then I can write it half of this with this and half of this with this, and so I can get integral 0 to pi 1 plus cot theta plus phi by 2 by phi d phi plus 1 by 2 pi 0 to pi 1 plus cot theta minus phi by 2 by phi d phi. So, this is how we arrive here by distributing half of this with this integral, half of this with this integral. So, this is how we come to this place, and then we can write it as, now let us combine the two integrals. Okay, so what we will do again, let us call them as say again I1 and I2. Let us place phi y minus phi in I1, replacing phi y minus phi in I1, we shall have I1 equal to 1 over 2 pi minus phi 1 plus cot theta minus phi by 2 by minus phi d minus phi. Okay, d minus phi is minus d phi, so I can write it as 1 over 2 pi minus pi to 0 1 plus cot theta minus phi by 2 by minus phi is equal to by phi. So, we get this. So, I1 is 1 over 2 pi integral over minus pi to 0 1 plus cot theta minus phi by 2 by phi d phi. So, this integral can be replaced by that, and then we can combine. So, replacing the value of I1, we have f theta equal to 1 over 2 pi integral over minus pi to pi 1 plus cot theta minus phi by 2 by phi d phi. So, we get this f theta equal to 1 over 2 pi integral over minus pi to pi 1 plus cot theta minus phi by 2 by phi d phi. From the first alternative pair, we recall that the second equation there is by theta equal to 1 over 2 pi minus pi to pi cot phi minus theta by 2 f phi d phi, and also we recall that f theta is an even function of theta. So, I can write this equation also as by theta equal to 1 over 2 pi minus pi to pi 1 plus cot phi minus theta by 2 f phi d phi, because the integral over minus pi to pi f phi d phi is equal to 0, because f phi is an odd function. So, this integral is same as this integral. So, corresponding to this form, we have the corresponding to this form of the integral equation, we have this as the solution of the integral equation. So, the relations 1 and 2 together give us the second alternative form of the finite Hilbert transform pair. There is one more alternative form which we call third alternative form of Hilbert transform pair. Let us recall that finite Hilbert transform of a function by phi is defined as this, f theta equal to 1 over pi integral 0 to pi sin theta over cos theta minus cos phi by phi d phi, where the inverse is given by theta equal to 1 over pi 0 to pi sin phi over cos phi minus cos theta f phi d phi plus 1 over pi 0 to pi by phi d phi. So, this is the first, this is the Hilbert transform pair. Let us now derive the third alternative form of this. What we do is we introduce the change the new variables u by equations u equal to cos theta and b equal to cos phi, and also we define the functions pu equal to f theta over sin theta. So when u is cos theta, theta will be cos inverse u. So f of cos inverse u we have, and then sin theta will be equal to under root 1 minus u square. Here we have this integral. In these integrals we will make the change of variables. So we are defining pu and qb, and qb is equal to we define as by phi over sin phi. So by phi over sin phi is by cosine inverse u, cosine inverse b divided by under root 1 minus b square. Now with this change of variables, let us see what we get from the first equation. This equation number 3. So f theta is equal to one over pi 0 to pi sin theta over cos theta minus cos phi by phi d phi. Theta is independent of phi, so I can divide this equation by f sin theta. So I get f theta upon sin theta equal to 1 upon pi integral over 0 to pi 1 over cos theta minus cos phi by phi d phi. B equal to cos phi gives us dB equal to minus sin phi d phi. So let us replace the value of d phi here. So this will be equal to 1 over pi. The limits of integration will become cos theta is u, cos phi is b. By phi is by cos inverse b. By cos inverse b, and d phi is equal to dB upon minus sin phi and here the limits of integration will become 1 to minus 1. So we can write it as 1 over pi minus 1 to 1 1 over u minus b by, and sin phi is equal to under root 1 minus b square. This will be by phi, okay, I can write it as by b, I can write it as by b over or I can say by phi over, by phi over, phi is cos inverse b, so phi over sin phi I can write dB, they are same things, okay. So this is nothing but phi, you can keep it as phi, let me write it as phi, okay. So by phi over sin phi we can write as qb, so 1 over pi minus 1 to 1 1 over u minus b and then qb dV. So pu is equal to, and u varies from minus 1 to 1 because theta varies from 0 to pi. So minus 1 less than u less than 1. Now, so pu, this first equation f theta equal to this can be rewritten as this f theta upon sin theta is pu. So pu equal to 1 over pi integral over minus 1 to 1 qv over u minus b dv. This equation is also known as airfoil equation. Now Similarly, let us go to the second equation. This equation by theta equal to 1 over pi 0 to pi sin phi over cos phi minus cos theta f phi d phi 1 over pi 0 to pi by phi d phi. So, let us write the alternate form of this now, making use of this change of variables. And what we will get is Qu equal to this. Let us see how we get this Qu equal to 1 over pi integral over minus 1 to 1 like this. So, what we do is we again divide by sin theta. So, by theta upon sin theta equal to 1 over pi integral over 0 to star u pi sin phi upon cos phi minus cos theta 1 over sin theta f phi d phi plus 1 upon pi 0 to pi by phi upon sin theta d phi. Now, QB is 1 upon by phi over sin phi. Okay. So, when we have y theta over sin theta, we shall write Qu because u is a function of theta. So, by theta over sin theta we shall write as Qu. So, this is Qu equal to now here 1 over pi d phi. What do we get? D phi is equal to sin phi d phi is equal to dB. So, sin phi and d phi we write as minus dB, and this is f of phi. Okay, so we can write it as minus dB for sin phi d phi, and here we will write cos phi minus cos theta. Cos phi is equal to b minus u. What we are left with? F phi. F phi is equal to PB over PB into sin phi, because b is a function of phi. So, PB is equal to F phi divided by sin phi. So, F phi is PB sin phi the limits of integration will be cos phi is equal to b. So, they will be 1 to minus 1, and we shall have sin theta here plus 1 over pi here also by phi is equal to QB sin phi. So, we have phi, the limits of integration for phi are 1 to minus 1, and y phi is equal to QB sin phi over sin theta d phi. Sin phi d phi is minus dB. So, this will minus dB we will get, and this will change to minus 1 to 1, and we will have this as 1 over pi minus 1 to 1. This will be sin phi is under root 1 minus b square, sin theta is square root 1 minus u square, and what we will get then, Pb upon b minus u square root 1 minus b square upon 1 minus u square into dB. This is for the first integral, and second integral will be 1 over pi minus 1 to 1 qb dB over under root 1 minus u square. Sin theta is under root 1 minus u square. So, let us see what we have. Okay, so now what we will do is, because this u is independent of v, so we can also write it as qu equal to 1 over pi minus 1 to 1 Pb upon b minus u under root 1 minus b square upon 1 minus u square dB plus c upon under root 1 minus u square, where c is the integral 1 over pi integral minus 1 to 1 qb dB. So, so q is equal to 1 over pi minus 1 to 1 under root 1 minus b square upon 1 minus u square Pb upon 1 minus b minus u dB, and then c upon under root 1 minus u square. C is given by this expression, which is an arbitrary constant. Now, this equation which gives us the solution of the integral equation, this together make a Hilbert transform pair, third alternative form. So, this equation is the equation where we are looking for the solution, that is the function q, and that solution is given by this equation. So, the equations 5 and 6 together give us the third alternative form of the finite Hilbert transform. Now, let us go to the definition of infinite Hilbert transform. The infinite Hilbert transform is defined as f(x) equal to 1 upon pi minus infinity to infinity by t over t minus x dt. You can see here that f(x) equal to 1 over pi minus infinity to infinity by t over t minus x dt. This is nothing but the right hand side is the convolution of the function phi t, the convolution of the function by t with the function 1 over pi t. So, the right hand side is the convolution of the functions by t and 1 over pi t. If you recall how we defined the convolution of two functions f t and g t. Convolution of two functions f t and g t is defined as f star t, f t star g t equal to integral over minus infinity to infinity f t g t minus x dt. So, right hand side is the convolution of by t and the functions 1 over pi t, and its inverse, that is the solution of this integral equation, is given by x equal to minus 1 over pi. So, solution is by x equal to minus 1 over pi integral over minus infinity to infinity f t over t minus x dt. So, the unknown function in the integral equation y t is determined by the the equation giving us the inverse, that is y x equal to minus 1 over pi integral over minus infinity to infinity f t over t minus x dt. I will take a question and see how we can solve this. Let us look at this homogeneous integral equation, because here the function f(x) is taken as 0. So, let us go to the third alternative form, Hilbert transform pair, this one, third alternative form of the finite Hilbert transform pair. So, Pu actually is taken as 0 here in this example. This is the case of finite Hilbert transform, not of infinite Hilbert transform. So, in this equation, if we are given that integral over minus 1 to 1 principal value of the integral qb dv over u minus b is equal to 0. Now, let us compare it with the third alternative form of the finite Hilbert transform. So, this is the equation Pu equal to 1 over pi integral over minus 1 to 1 qv dv upon u minus b. So, if you compare the given equation with this equation, we have Pu equal to 0. Now, let us see the solution of the integral equation is given by qu equal to 1 over pi integral over minus 1 to 1 under root 1 minus b square upon 1 minus u square pv dv divided by b minus u plus c upon under root 1 minus u square. U belongs to minus 1 1. Now, we know that from this equation, we know that Pu equal to 0 over the interval minus 1 to 1. We are given that Pu equal to 0 over the interval minus 1 1. So, let us put it in this equation. Pu here we put Pu equal to 0, the PV varies from minus 1 to 1. So, the first expression becomes 0 and what we get c upon under root 1 minus u square. So, where c is the c is given by c is an arbitrary constant 1 over pi integral over minus 1 to 1 qb dv. So, here the solution of this equation, the homogeneous integral equation is given by qu equal to c upon under root 1 minus u square. So, this is how we solve this example by making use of the third alternative form of the Hilbert transform pair. With this, I would like to conclude my lecture. Thank you very much for your attention.